Okay, so last time we were just beginning to build more complicated molecules. Our first 3-atom molecular orbital example is shown here. This is where we ended, where we did the molecular orbital diagram for H3+. And remember, what we're doing in these cases is we're going to break the molecules up into group orbitals and then a central atom, center atom. And what we did here is we used the 2 outer hydrogens as our set of group orbitals, right? 1s orbitals from each of those outer hydrogens. And the center hydrogen is the central atom. And we found what the symmetries are going to be just by inspection of these group orbitals in the center atom orbital. And then we mixed them according to their symmetry matching. And we came up with this picture where we have either even under inversion or odd under inversion kinds of symmetry. And so we had 2 group orbitals, 1 center atom orbital. That's 3 overall orbitals that we need to build. So we have our 3 molecular orbitals, 1 bonding, 1 pure non-bonding because it doesn't symmetry match the center atom orbital at all, and 1 anti-bonding. And this was also our first example of a 2-electron, 3-center bond, where, as a very common theme in molecular orbital theory, we have delocalization of electrons, bonding electrons, anti-bonding electrons, over either the entire molecule or substantial fragments of the molecule. And we can pick that up right away just by looking at the wave function, for example, for the bonding orbital here. It has equal contributions from all 3 atoms. Those 2 electrons are delocalized equally between these 3 atoms. Okay? So that's something that we're going to see time and again as we develop more and more complicated molecules. The next step in adding complexity here would be, of course, to add in p orbital interactions rather than just have a chain of hydrogen atoms, which is kind of fun. We can include other atoms, second row atoms, that have p orbitals. And so our next example is going to be fluorine H, fluorine minus, another ion here, linear ion. And in this example, we have a center atom which has just 1 s, so we keep the simplicity there. But the outer group orbitals are going to be composed of s and p orbitals now. Okay? So let's see how this is going to play out. And it's basically just an extension of what we did for the hydrogen chain. We can right away say that for the central ion in this case, the atom, we have, as before, just a 1s orbital to worry about. And it comes in, let's say, positive. Okay? So it's going to have Ag symmetry. It's totally symmetric with respect to this particular point group. Okay? What about the outer atom orbitals, the group orbitals? To do this, we can do this by inspection again. So what we're going to do is basically just look at it and intuitively say how we could get these different orbitals. Okay? What we first have to do is assign a set of axes to the molecule. And we assign the z-axis as normal along the internuclear axis here. In this case, the x and the y are painted as they are in that figure. Okay? We have 2s orbitals and the 2 p orbitals, the 3 different types of 2 p orbitals coming in from each fluorine. So each fluorine has 4 valence orbitals we need to worry about. That gives us 8 total orbitals. Okay? And because we only have 2 fluorines, it's again quite intuitively easy just to figure out how they must look, okay? How they must sum to give the group orbitals. If we look at the 2s orbitals for the fluorines, so this is notation here. This is 1 fluorine on the side, the other fluorine on the other side, and nothing at the hydrogen position. Okay, we can either have the 2s's come in phase, or we can have them come in out of phase, right? Either the sum or the difference. And so we have the sum that's shown here. The other group orbital that's going to be from the fluorines is the difference. Okay. Next to the sum and the difference, we have the irreducible representation labeled. And I'll show you how we can easily generate this in a second. The Ag is simple to generate. You can see right away that it's totally symmetric. Okay? The sum of the 2s orbitals. We'll show in a minute how we get the B1U designation. Okay? Out of the character table is where it comes from, of course. The other sigma type interaction that's going to be generated is from the 2pz's. Okay? So we have the 2pz, which is going to be Ag, again, totally symmetric. This is the difference. And the sum gives us another B1U. So the symmetry of the s's and the pz's are the same. We have 2 group orbitals from each of the s and the z's, the pz's. And each one has an Ag and each one has a B1U. The others, the py's and the px's, we can either have them in phase or out of phase, in phase or out of phase, right? The sum or the difference. That's the only two ways, those are the only two ways to make these sorts of linear combinations with two identical orbitals like this. And we've labeled the irreducible representations as such. Okay, so you can see we have a number of different irreducible representations that are coming in from the group orbitals this time, which is where the added complexity comes from. Okay? Where do these symmetry labels come from? Well, you take a glance at the D2H character table, and you look at how each of these orbital configurations transforms upon every symmetry operation. And you can deduce that, for example, this one is B1U. Okay? So let's look at the easiest. Let's look at, for example, this one here, this AG. We look at this set of this difference of the two p orbitals here, and we look at all the different symmetry operations and determine whether it stays the same or whether it inverts. Okay? So under E, of course, it stays the same. The C2 axis is along the internuclear axis, so that's this direction, so it stays the same. The C2y and the C2x are the other two axes, and you can see that if you flip 180 degrees around the axis that's coming out at you, it stays the same. And the axis that's in the plane this direction also stays the same. Inversion doesn't change, right? The negative lobes interchange, the positive lobes interchange, it's unchanged. And same thing for the three reflection planes, okay, the perpendicular reflection planes. Gives you an unchanged situation, and so that's why that's AG. This one's easy to see it's AG. This one's maybe a little bit more difficult to see that it's AG. But that's how we would assign the symmetry labels. So let's look at one that's not so simple. Let's look at the B1U here. This is the difference in the two S's from the fluorines. Why is it labeled B1U? Well, we can go down the different symmetry operations. Under E, nothing happens, of course. Under C2 along the Z, it's unchanged, and so it's a character of 1. Okay? So far that's consistent with B1U. Under the C2 along the Y, we have a switch. Okay? Let's say that the C2 is coming out at you. And if you rotate 180 degrees, we have multiplied that function by -1. So it gets a character of -1. Same thing for the x-axis. If this is the x-axis here, we rotate around that. Again, it's antisymmetric. So we have a -1 character. Inversion, it flips. One of the reflection planes it flips, the xy reflection plane, is this plane right here that comes out at you and through the board. That causes the symmetry to be antisymmetric. And the other two are the same, right? The other two have perfect symmetry under that operation, right? So reflection plane in this direction and in the perpendicular direction. And so by looking at the shape of the orbital that we've constructed and walking, if you need to, along all of the symmetry operations, you can assign which irreducible representation that particular group orbital has. Okay? And that's done for all of these 8 group orbitals that come in from the fluorines. This one is the same as that one. You can tell the 2 and the 3, okay, indicate whether, which of the C2 axes is symmetric and which is antisymmetric for that particular set of orbitals. Okay? And then we also have, in this case, U and G designations because we have an inversion center, right? And we need to distinguish whether it's even or odd, in other words, symmetric or antisymmetric with respect to inversion. Okay? So that's how we would generate all the symmetry labels. And why do we care about the symmetry labels? Well, we need to know the symmetry labels so we know what orbitals from the group atoms, from what group orbitals from the outer atoms are going to be able to interact with the center atom orbital. Okay? And so we have our orbitals here. We should have 9 orbitals altogether that we need to worry about. Okay? And that's what we've got. Now let's look at what can interact with the center atom. Okay? We basically have 2 group orbitals that we expect by symmetry can form in principle bonding and anti-bonding combinations. So all of the other interactions, these should all be basically non-bonding combinations. Okay? And so by symmetry alone, we expect an interaction with group orbital 1 and group orbital 3. The question we always then have to ask ourselves is, symmetry allowed, yes, but what about energetically favorable? Right? Are the energies similar enough to actually expect significant interactions? Okay? So symmetry tells you what can happen. The energy tells you more about whether something will actually happen if it can. Okay? So let's look at our picture now. We have to consider the energies again, and we have H and we have F. And so we've done this problem before, right, when we just looked at HF itself. And we expect, again, since the fluorine 2s's are so deep in energy, there's going to be basically no interaction with the hydrogen. Okay? The main interaction is going to be between the hydrogen and the p orbitals. And so that means if we go back to our picture here, the interaction between this orbital here, which is s from the fluorines, and the center atom is going to be minimal to 0. Okay? And the main bonding and antibonding interaction we expect is going to be from the pz's and the center 1s orbital on the hydrogen. Okay? So this allows us to construct the basic game plan in our mind before we even have to write down anything to draw the molecular orbital diagram. Okay? We kind of know what to expect. Okay. So this is just pulled from your book, and this is the finished molecular orbital diagram, so we can walk through it here. Okay? So what we have is, as always, the center atom is going to be on the left, so that's hydrogen. The group orbitals from the fluorines coming in on the right, and then the molecule or the ion that we're making is in the middle. Okay? Hydrogen has just the one s orbital. In this case, it's negative 13.6 electron volts. We have from the two fluorines, we have, of course, the 2 different combinations of the s orbitals, and we have the 6 different combinations of the p orbitals. Right? 2 combinations each for the px, py, and pz. The s orbitals are at the same energy. The p orbitals are at the same energy. This is because, again, the fluorines are separated by hydrogen, so they are considered to be far enough away from each other that there's no interaction between the fluorines. Okay? So the orbitals are unchanged in energy relative to the individual atomic orbitals of fluorine. Okay, and so now let's see what happens. So we said, based on the symmetry argument, that we expect only bonding and antibonding combinations to happen when they are Ag, right? Everything else is going to be non-bonding. But because these fluorine 2s's are so deep in energy, the interaction is going to be very minimal. And so basically what we would do is we would draw both of these s orbital combinations as coming over and being almost completely non-bonding. Okay? Definitely non-bonding for the B1U, but almost totally non-bonding as well for the Ag set of s orbitals. Okay? And so essentially these are going to come over and just rest here. You can see that they are a little bit decreased in energy relative to the s orbital original energies. This is because of orbital mixing, and we'll get to that in a second. Okay? This is the step that we might do at the very end of the molecular orbital diagram construction process, where we consider orbital mixing, and that's going to, in this case, decrease these energies very slightly. Okay? But for the most part, these are non-bonding. Okay? We always begin the molecular orbital diagram construction by looking at sigma-type interactions. This is always the easiest, and then pi-type interactions. Okay? So we look first at our s orbitals to see what kind of sigma interactions they have. Next, let's look at the p orbital interactions, sigma-type. Okay? And as we said before, the symmetry of the 1s is Ag, and we have an Ag representation also for the 2pz's. Right? They're close enough in energy to significantly interact, and so we're going to get a bonding and an anti-bonding combination. Okay? So the bonding combination has this sort of flavor to it, where we have the hydrogen in the middle here, and we have this 2pz combination, right, which is the Ag combination. You probably can't see it in the back, but this is very slightly shaded gray here, and that's white, and that's gray. And so this is the difference of the 2p's, and this gives us the Ag representation, right? The one that can interact with the center hydrogen. So we get our bonding, we get our anti-bonding. Okay. All of the other orbitals don't have a symmetry-matched pair on the center atom. So all of the other 5 p orbitals, the group orbitals, should just come over and be non-bonding. And you can see that in this finalized diagram, 4 of them are completely non-bonding, but 1 of them has been kicked up slightly in energy. This is again because of orbital mixing. Okay? And I'll describe that in just a second. Okay? The wave functions are drawn here for the molecular orbitals. Okay? So the bottom one here is the totally symmetric. We call these, the convention is to use lowercase characters to indicate the symmetry of the molecular orbital. So we know that this is an Ag, capital Ag, in the irreducible representation. In a molecular orbital diagram, typically you have baby Ag, or lowercase ag, to indicate the symmetry of that molecular orbital. And you would label them as the first AG, the second AG, the third AG as you go from the lowest energy to the highest energy orbitals. Okay? That's not done here, but we'll do that later. So this is we could consider this to be 1 AG, the first AG. Okay? Then the next one in line here is the B1U that's coming in from the 2s orbitals on fluorine, right? But it has no interaction at all with the hydrogen, so it just comes over. It's a pure non-bonding orbital. Okay? And the others. This is the second AG, that's the bonding one. This one appears the third AG, the anti-bonding one. And then we've got the various P-related, the PX, PY-related orbitals coming in. Okay? That's how they would be painted. And these are actually real calculations, not just shading diagrams. Okay? These actually have some more reality to them. Okay, so we essentially expect non-bonding, bonding, anti-bonding, and all these to be non-bonding. But as I mentioned, we have a little bit of orbital mixing. Why do we have orbital mixing? It's because, as you might remember, anytime you have molecular orbitals that have the same symmetry, right, and different energy, they will interact a little bit and they will cause the lower energy orbital to decrease slightly in energy and the higher energy orbital to come up in energy slightly. So we have to look at the symmetries of our molecular orbitals and find out, do we have any matches in the molecular orbitals? And we definitely do, right? So we have AG, AG, and AG, okay? And so even though this AG here is really got very, very small interaction with hydrogen because of the big energy difference, it's going to orbital mix with this AG and a little bit less with this one, and that's going to cause the bottom AG to decrease in energy slightly. Okay, so that's this orbital down here. You can see it's been pushed down in energy. That's because of the orbital mixing phenomenon. It looks like the same thing is happening with the B1U, and why is that? Well, there's a B1U here, and there's another B1U up here. Okay? So two molecular orbitals with the same symmetry, they can interact. And this B1U is forced down in energy a little bit, and this B1U is kicked up in energy from its original energy, which was here, kicked up in energy slightly. Okay? And so that's kind of putting the fine-tuning completion on this molecular orbital diagram. The others, these four MOs here, and well, just these four, have absolutely no other molecular orbitals that have the same symmetry. And so they come across with their energy unchanged. Okay? And then we can fill in the electrons if we want to. We can understand some degree of or some amount about the bonding in this molecule or this ion. And so what do we have? We're going to have how many electrons? We're going to have 16 electrons in this particular molecule, right? 7 from each of the fluorines, plus 1 from the hydrogen, plus 1 from the charge. And so we have 2, 4, 6, 8, 10, 12, 14, 16 electrons. Okay? And if we want to answer questions about what the HOMO is, what its character is, what the LUMO character is, and so forth, we can do that. Okay? So this is the basic idea just by doing it by inspection. Anytime we have a very simple molecule, especially with 2 atoms as the group orbitals, contributing to the group orbitals, we can pretty much build a molecular orbital diagram without using any formal procedure. We can do it just by looking at the problem. Questions about this example? Yeah?
I'm just curious. So for those 4 degenerate orbitals, why 2 of them actually have nodes, but why their energy?
So these guys here, yep. So they all have nodes, right? And they should have about the same number of nodes to be about the same energy. Sometimes it's difficult to tell based on just the wave function drawing that they should be the same energy. For example, if you look at dz squared and dxy for an isolated metal atom, for example, they don't necessarily look like they should be isoenergetic, but they are. So in this case, there's the same number of nodes in those configurations. And because another way you can think about it is because they're made from the same orbitals, right? They're all p orbitals. And because the fluorines are not interacting with anything, they're too far away from each other to interact, and they have no symmetry allowed interaction with the hydrogen, then you basically have, no matter what the sign is of the molecular orbital that you're drawing, it's going to have the same energy. Right? They can come in as the sum, they can come in as the difference. it doesn't matter because they're not feeling each other. That's one way to think about it. Yeah. Other questions? Okay. Okay, so you can probably guess where we're headed to next. Okay, we have one more linear example. We've gone from all 1s orbitals. Then we went to an example where we have p orbitals that we're considering on the outer atoms, but still just an s orbital on the center atom. So the next example is where we consider s and p orbitals on all 3 atoms, right? And so the number of interactions is going to be quite different. Yeah, I have some more stuff on this slide here, so let's look at this really quickly. What does this tell us about the bonding in this particular ion? Well, we have one strong sigma bond. We have something that we can consider a very, very weak bond. So this would be like, how many bonds does this molecule have, or this ion? It has 1 plus delta. Okay, it has 1 plus some small amount. Okay. We also then have non-bonding. The others are all non-bonding. So does this agree with the Lewis dot diagram? Well, sort of, right? So we can see that we have 6 non-bonding pairs, and that's equivalent to what we see in the Lewis dot diagram. But the bonds, we have one what we would call a real bond, or a significant bonding interaction, and we have one that's basically very, very weak. Right? And that's not necessarily in agreement with the Lewis dot picture, where we have 2 equivalent sigma bonds labeled in the Lewis dot picture. So again, we have a more nuanced version of reality here when we consider the molecular orbital diagram. And what we can say is that we have, again, another 2-electron 3-center bond here. And we have another set of electrons that's sort of floating around between the 3 atoms as well, but not contributing that much to the bonding. So you could say from the molecular orbital diagram that we have 1 plus something bonds, and we have something more than 6 lone pairs. So you get into these fractional ideas. And this is because we have delocalization of electrons, and so you cannot assign any more particular 2 electrons to a particular bond. It just doesn't really work that way. Reality is more nuanced. And we have, because we have quantum mechanical objects, we have delocalization of these things over the unit of the molecule. Okay. And again, the 2 bonds here, the Lewis dot picture assumes that they're the same. Definitely they are not the same. They have very different energies and very different bonding characters. Okay. The final linear example that we want to look at, 3-atom, is carbon dioxide. So we've looked at carbon monoxide. Carbon dioxide's a bit more complicated, but because of what we just did for the fluorine 2 hydrogen minus ion, we've already set up most of the problem. Okay, we're going to again do this by inspection first, and then we're going to come back to this example in a minute, and we'll do it with our more rigorous 6-step procedure, okay, that uses explicitly uses the character tables. So here's CO2, same set of coordinates that we used for the previous example. Same idea, center atom, outer atoms. The outer atom group orbitals are exactly the same as those that we put down for fluorine. Okay. They have a different energy, certainly, but the shapes and the irreducible representations that correspond to these different combinations are identical to what we just did. Okay, so we just regurgitate those 8 here. How many do we have from carbon? Well, of course, we've got the 4 from carbon, right? The 2s and the 3 2p orbitals. We can again assign their irreducible representations, their Mulliken labels, quite simply. In this case, you can do it because this is the center atom. You can just look at the character table. S is always AG. It's always totally symmetric. And then you can just look for the x, y, and z functions in the character table. And that gives you the px, py, and pz. Okay. Or you can go through the whole procedure of looking at all the individual symmetry operations and convincing yourself that this should be B1u, B2u, and B3u. Okay. I find it easier just to look at the character table and pull off x, y, and z. That only works when the atom is at the center of the molecule, for the most part. Okay, so we have 12 molecular orbitals to look at, right? 12 total orbitals that we're going to build. How many different symmetry matching combinations do we have here, right? How many different bonding and anti-bonding combinations do we expect to see? Well, let's take a look. Again, we have the AG like we had last time. We're going to have an interaction in principle between these 3, leading to bonding and anti-bonding combinations. What about B1U? Well, there are 2 B1Us here and a B1U there. So we're going to have those 3 interacting. And do we have others? Let's look at the B, well, I think I go here, B2U. Aha, there's a B2U. So we're going to have interactions there. And B3U, yes, right? We have a match there as well. So all of the center atom orbitals, in principle, can interact and form bonding and antibonding combinations. That leaves two group orbitals here, the B2G and the B3G, without any symmetry matching pair. And that means that those are going to be non-bonding. Okay? So we expect to have two non-bonding, pure non-bonding MOs. And the others, we're going to have a pretty complicated diagram. Okay. Here again are our energies. Remember that the oxygen is not going to interact, the oxygen 2s is not going to interact very well with the carbon 2s because of this large energy difference. But remember that the two carbon sets of orbitals here can interact with the oxygen 2p quite nicely. So this again sets the stage. The oxygen 2s should not interact very well with the carbon 2s. All right, so here we go. We're actually going to build this one up using our normal animated building process. So here's carbon, and here's our two oxygens. Okay, carbon's center atom, it's on the left, group orbitals on the right. Carbon has 4 valence electrons. Here's basically a semi-qualitative drawing of its energies. Okay, s orbital, p orbitals with the shading drawn. And then the oxygen, since we have 2 of them, we have 8 orbitals altogether, right? We have the 2 s-related ones and we have the 6 p-related ones. They're all the same energy because, again, they're too far away from each other to feel each other. And until we interact them with the center atom, they are degenerate. We start with looking at sigma-type interactions, and then we move to pi interactions. Okay, so let's start with sigma interactions. Easiest thing to do is to bring in the symmetry labels so we actually know what orbitals are going to interact with what. Okay, so these are just pulled from the 2 slides ago. So we have here our Ag on the carbon, and we have an Ag down here, and we have another Ag up here, right, in the P and the s orbitals for the oxygens. Okay, let's do sigmas. So sigmas are going to look like this for the Ags. Right? So we have the 1 from carbon interacting with 2 from oxygen. So we have 3 molecular orbitals that we need to build. And what we're going to have is down here the most bonding, or the deepest energy, I should say, sigma-type interaction is mostly oxygen in flavor because it's closer to the oxygen orbitals. Right? And it's going to be a bonding-like interaction. So it's just 3, the same shade, with a smaller lobe coming in from the carbon. Okay, the center atom having a smaller contribution than the outer atoms. This orbital is going to be almost purely of an S flavor, right? And so its lobes look like circles. The second orbital, next one up in energy here, is going to be mostly carbon related. So it's carbon interaction with its 2s and the 2pz orbital, the Ag1, from the oxygens. The orbital is going to have the proper shading, of course, for making a combination for Ag. And it's mostly going to have the biggest lobe on carbon there. And then the highest energy of the Ag set is going to be mostly oxygen. Okay, so we have larger lobes for the p orbitals there. That's what's shown. And it's, again, Ag. So you can verify that. If you can't see it in the back, right, it's just taking this orbital here and flipping it around. So we have dark, light, light, dark, and then the center lobe for the s orbital for carbon is dark. So again, that's still an Ag interaction. We can label these with the symmetry of the molecular orbitals. And I start here by labeling this as 2Ag. That's because there are 1s orbitals, right, in these atoms. They would be called, they're going to be totally non-bonding because they're so far apart from each other, but that would be called the 1Ag, the one that we haven't drawn, the 1s related ones. Okay? We're just dealing with the valence orbitals right now, right? So we call this the 2Ag, the next one up the 3Ag, the last one the 4Ag. Okay? Again, to indicate the symmetry of the interaction and its relative energetic order. Okay, so we've got those Ags. What about other sigma-type interactions? Right? Well, we have interactions from the pz orbitals between the 3 different molecules, the 3 different atoms. Okay? And this is, again, because we have pz's interacting in line, we're going to have sigma-type interactions. That's why we're considering these next. We're going to have interactions between the B1U PZ and its symmetry matched pair, the B1U from the PZs on the oxygens. We make a bonding, we make an anti-bonding combination. Okay? And it's hopeless to see the shading in the back now, but this is bonding and that's anti-bonding. And we can label, And so these are the two that are interacting, right? But we have another B1U that's down here. The B1U here does not interact with this B1U from the carbon because the two P's on carbon are way too far in energy from the two S's on oxygen. And so the two S's on oxygen, this particular B1U group orbital is just going to be non-bonding, and it just comes over. Okay? It again will be slightly perturbed because of orbital mixing, but for now we just bring it over directly. Okay? So then we can label these. We would call this the second B1U because there's a 1s related B1U that's down deeper in energy. This is the third B1U, and then the fourth B1U is up here. Okay? All sigma type interactions. At this stage in the game, we've accounted for all the sigma bonds and antibonds that we expect. Because we've looked at the S's and we've looked at the PZs. And what's left is to look at the PYs and the PXs. So what we're going to do here is shade out the stuff that we've just looked at because there's a lot of lines that are coming in. Right? So those are our set. We'll leave those alone for a second. And now let's focus on the remaining orbitals. Okay? So the orbitals that we've accounted for are grayed out. So those lines are grayed out. These two lines are grayed out, the PZ-related lines. Right? This is a PZ, it's gone, and the S is gone. What we have left are interactions between B2U. Where's our B2U? There's our B2U here. Our B3U. Here's our B3U. Okay? And then we have two additional orbitals from the P's on the oxygens that have no symmetry pair, right? The B2G and the B3G, which have no representation over here. So let's look now at the bonding and antibonding. Now these are the pi orbitals, right? So we expect bonding and antibonding pairs. The PX and the PY are going to have degenerate energies because they're symmetrically identical. So we have bonding, we have antibonding. We can label them. One of these is the B2U, so this is the first B2U, and its antibonding partner is the second B2U. The other one is a B3U, the first one, and the second one up here is the second B3U. Okay. And those are then corresponding, of course, to the pi bonds once we fill up the electrons in this molecule. And we should see pi bonding in carbon dioxide. So that takes care of all of the center atom orbitals then. We have accounted for the AG interactions, the B1U interactions, and the B2U and B3U interactions. And so I don't know if I grade them out next. No, I didn't. But you would grade these out now and grade this one and this one out. And all that's left to account for are the non-bonding group orbitals, the B2G and the B3G. Those just come straight over. They have no interaction with the center atom at all. And so they should just sit there unchanged in energy. Okay, and we can label those two, the first B2G and the second and the first B3G. Okay. We had 12 orbitals altogether that we needed to worry about. 8 from here, 4 from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. And so we are done. Right? We can then modify slightly with orbital mixing if we wanted to make it a little bit more accurate. But for the most part, the basic molecular orbital picture for carbon dioxide is now set. Okay, so let's pull all this orbital jazz off, all this symmetry information off so we can clean it up a little bit. We've got to now fill in our electrons and try to understand what bonding should look like in carbon dioxide. So we fill in our 12 electrons, our 16 electrons, excuse me. So we have 12 from the oxygens and we have 4 from the carbon. Okay. 2, 4, 6, 8, 10, 12, 14, 16. All right, so far so good. Now let's look at the kinds of bonds that we have. Okay. And this is how I've labeled it here. We have clearly a very nice, strong sigma type bond from the two PZs interacting. This other bond here that's got character from the 2PZ on the oxygens and the 2S on the carbon is also sigma type bonding. Okay. It's in the intermediate region, right, of energies, and so you can't tell necessarily just by looking at the position relative to the carbon that it's bonding. but it definitely is. It's just been pushed up slightly when we add the orbital mixing. Okay? So that would be considered, those would be considered the 2 sigma bonds. We have 2 pi bonds. Okay? So we have the px and the py interactions yielding 2 pi bonds. And then the rest of the bonding, these guys here are non-bonding. This one is non-bonding. And this one that's really deep in energy is also essentially non-bonding. If you look at its wave function here, most of the electron density is going to be on the oxygens with very little on the carbon. And that's also consistent with the very deep energy of the oxygen 2s's, even relative to the carbon 2s. Okay, so this difference here is about 13 or so electron volts. Okay, and so that's going to be a small interaction, certainly. And so we can consider these 4, these 2 up here, non-bonding, these 2 down here, non-bonding, with this one essentially non-bonding, this one rigorously non-bonding. Okay? And so what do we then have for CO2? Whoops. We have, like we would expect, 2 sigma bonds between the carbons and the oxygens. We have 2 pi bonds between the carbons and the oxygens, accounting for the 4 total bonds in CO2. And we have 4 lone pairs, and if you look at where the lone pairs are, this lone pair is only on oxygen, these lone pairs are only on oxygen, and this lone pair down here is mostly on oxygen. And that again accords well with the Lewis dot diagram where you have 4 lone pairs on the electronegative oxygen and you have 4 bonds. Okay?
So if we were talking about mixing, because we have the 2Ag, 3Ag, and 4Ag,
Yep.
how are they, like,
So in this case, the easier ones to understand are the end members, the low one and the high one. Those are going to be dropped down and raised up by some amount. The one in the middle, you can think it could rattle either way, right?
Yeah.
So it might be pushed up, it might be pushed down. It's impossible to tell just by looking at the level of detail that we're considering here.
Okay.
Yeah, you have to actually calculate it. Yeah.
So if we were like drawing it, like how would we know if it's lower than the
Yep. Yeah, so exactly where it's located in energy. Is it up here? Is it down here? You would not know. You can't know. And so, you know, when we test on this sort of thing, what we're going to be looking for is the general ordering. Right? And so when it gets ambiguous, as sometimes it does for these multi-electron atoms, you know, there's no way for you to know. You can use things like the number of nodes in the molecular orbital to get some idea. But if you have interactions that are different, you know, some interactions that are from mostly p-type and another interaction that's mostly s-type, it becomes very difficult to tell just by looking.
Okay.
Yeah.
But, so we can't tell at all if, without calculation with relative to the atomic orbital. But what about the 2 pi bond? How would we know if it was higher than that or lower? Or rather the
So this is what you can know with some certainty. Okay, if you just look at the p relationships, the p interactions. Okay, we have a sigma and we have 2 pi interactions, right? The sigma interaction for the p orbital is here, and the pi interaction is here. That's the bond, the two different bonding interactions. We expect the sigma difference in bonding and anti-bonding energy to be larger than the pi because of the larger overlap integral that we see for sigma type interactions relative to pi. So the splitting for the pi's should be smaller than the splitting for the sigmas. And that's what's shown, right? So the splitting for the pi's is here, right? So that energy difference, bonding and anti-bonding energy difference. The splitting for the sigmas is here, right? And the splitting for the sigma is larger than that for the pi because of overlap. So that you can tell, but what you couldn't tell is where this is, this set of orbitals, the pi orbitals, relative to this one here. That's essentially impossible to know without actually calculating the coefficients for the wave function and calculating the energy, which we're not doing here. Yep. So this approach takes you only so far, right? So if you want more realistic numbers, and in particular getting the nitty-gritty order down, then you have to go to something that's more complicated than what we're talking about. And actually, interestingly, a lot of these questions remain very contentious arguments in the scientific literature. So even for some simple molecules, there are ongoing arguments about what exactly the molecular orbital order in energy is. When it gets very fine, it's very difficult to tell sometimes. And so this is still a very important part of molecular chemistry, is trying to work out exactly the order for many different molecules. Other questions? So you guys are on the leading edge here. Carbon dioxide. Okay. If we want to look at a more rigorous procedure for describing these molecules, we can go back. Instead of doing inspection, we can use our multi-step process that I showed earlier. Okay, and this is just shown again, where we determine the point group of the molecule, assign axes, and then get the reducible representations, reduce them, then do the interactions with the center atom, and generate our MO diagram. What I want to do, we did the inspection approach for carbon dioxide. What I want to do is this, in the last 10 minutes of class today, is this example again using the more rigorous approach. Okay, so we're going to do carbon dioxide again, but we're going to use reducible representations instead of just inspection. Okay. So what do I mean by that? Okay, we start exactly in the same way we did before. We use the D2H point group. This is a D infinity H molecule, so we reduce our symmetry. Descend in symmetry here. We assign axes, the same axes we already had for carbon dioxide, so that's not new. What's new here in the more rigorous approach is that we want to build reducible representations for the group orbitals. Okay? So instead of just saying, okay, because we have two oxygens, we can have the s orbitals coming in as the sum or the difference, right? Instead of doing that, and then trying to assign its irreducible representation, we can determine the irreducible representations straight away from the character table. So this is what we would do, okay? For any problem that's like this. You draw the character table or get the character table out of the book or whatever. So this is D2H. And here's all of our symmetry classes. And we need to make reducible representations for the valence orbitals of the outer atoms. So we can build these 8 group orbitals that we had before. That means that we want to look individually at a reducible representation for 2s and then the individual 2p's. Okay? And so in your mind, you put an s orbital on oxygen, another s orbital on oxygen. Okay? And you do the symmetry operations and find out what the characters are for all of those symmetry operations. And so for the 2 s's, if you have an s here and an s here, right, you have a character of 2 under identity. For the C2 along the z-axis, you have a character of 2. The orbitals move for rotations along the y and the x-axis, so you have a character of 0. Under inversion, they move, so you have a character of 0. Under an xy reflection, they move, character of 0. Under the other 2 reflections, they don't move, so you have a character of 2 for both. Okay? And you go through and you do the same thing for the p orbitals, the 3 different kinds of p orbitals, and you're going to get these particular reducible representations for those 3 kinds of p orbitals. And then what you would do is you reduce the reducible representation to its irreducible parts using the reduction equation that we've shown several times now. Okay? And so here's that equation again, right? The number of irreducibles that are present in the reducible representation can be figured out with this reduction equation. And we would do this for each of the 4 reducible representations that we have. Okay? And when we do that, you go through the math, or you can just do this directly because there's only a character of 2 here. You find that the reducible representation for the 2s is equal to an Ag and a B1U. That for the 2pz is also an Ag and a B1U. Okay? And then the x and the y's have a B2G and a B3G and a B3U and a B2U. Okay? And you can confirm this straight away by just looking at the character table. Let's look at Ag and B1U. Here's Ag here, here's B1U here. If we add the characters for Ag and for B1U, we're going to get this. Okay? So we'd have 2 along, for E, we'll have 2 here. For the C2 along the Z, we're going to have 0 because we have -1, +1 for the third one, and so forth and so on. Okay? So you can easily confirm that this set of irreducible representations corresponds to that reducible representation. And this should look very familiar. We've basically just used the character table to determine straight away, without doing any mental math, right, what the irreducibles are for the different group orbitals. And this is exactly what we showed before. Right? The s orbitals are A1G and B1U. The pz's are Ag, B1U, and so forth. Okay? And then this just cements the point. So we have our reduced reducible representations, right? The 8 different irreducible representations. That corresponds to exactly what we showed before. AGB1U for the S's, AGB1U for the PZs, and so forth for the other 2. It's like magic, right? It works very, very well. And so this is a totally reliable procedure for simple molecules anyway, to determine what the reducible representations are for the group orbitals if you would prefer not to do it by inspection. And in many cases, this is the vastly preferred way because you can imagine that when we start talking about nonlinear molecules, things get a little bit crazy, right? And so this is a way that you can always get the correct irreducible representations for the group orbitals. You can do the same thing if you want to get the group orbitals, or the atomic orbitals for the center atom. As I mentioned before, the by far easier thing to do, right, is to just look at the character table. So the character table tells you right away what the PZ, right, Py and Px orbitals are. So we should have B1U, 2U, and 3U for the P orbitals on the center atom. And the s orbital is not written down here, but the s orbital is always Ag, right? It's always totally symmetric under the point group operations. And so we should have an Ag and then B1U, B2U, and B3U, and that's what we have, okay, for the center atom. And then what we would do at this step is exactly what we already have done. We identify those that can match, and then we build our molecular orbital diagram considering the relative energies. And so we would get what we made already. Okay, we would get this picture. Okay. Let's apply this to our first bent molecule, nonlinear molecule. Okay. Water, an important molecule. We're not going to finish this example today, but we can get it started. Okay. So we're going to use, in the case of water, again, we can do it by inspection, but it's more fun to do it by the full procedure here. So water, you probably already know, is C2V, right? That's the point group of water. We want to assign axes to water. These are the axes that are assigned in your book. Okay, so this is fine. We consider, of course, the C2 right along the oxygen splitting between the hydrogens. That's going to be our z-axis. And then we'll use the zx plane as the molecular plane. The y plane is perpendicular to the molecular plane, or the y-axis is perpendicular to the molecular plane. Okay. So we set our axes. Setting our axes dictates which symmetry label is going to apply to which of the orbitals. It does not bias the problem. Okay, if we chose a different set of axes, we would get an equally correct but different set of irreducible representations, okay, just because we chose our axes differently. Your choice of axis cannot change the physical consequences of one of these problems. What do we do next? We bring up the C2V character table from the back of the book. Okay, it's simpler than the D2H, thankfully. And what we want to do is consider the group orbitals. And luckily for water, all we have to care about are the 1s's of the hydrogens, right? Because there's nothing else for the valence orbitals. So we need to build a reducible representation for the 1s's, okay, the hydrogens out here. Okay. Under E, there's 2 1s's that don't change, character of 2. Under C2, they both move. Under the reflection plane in the plane of the molecule, they don't move, right? 2. And then the perpendicular reflection plane, they do move, 0. We reduce this, and it turns out that the group orbitals are going to have symmetry of A1, okay, and B1. All right? So we have now our group orbitals using this simple procedure, and then we just need to figure out what the orbitals are on the oxygen. Why did I do that? I don't remember. So we'll go on. This is what the orbitals look like. We have 1s orbitals. We can either have the sum or the difference. Right? It's a very simple example. So for the A1, the totally symmetric, we have the sum. For the B1, we have the difference, and you can confirm that these are correct by just looking at the characters, or looking at the symmetry operations in the character table and confirming that they transform as they are specified in the character table. This little bent thing here with nothing there, this indicates where the oxygen is going to go, of course. Right? So we kind of draw it like this to indicate that we've got a bent molecule that we're building. And then in the final minute, let's see what we do next. We get the matching orbitals on the oxygen. Okay. How do we pull the oxygens off? Well, we can look at the character table. And we can find that we've got an A1 for the Z, that's a PZ. B1 is going to be the PX. B2 is going to be the PY. And an A1 is also going to be the S, because the S is always totally symmetric. And so here's our A1, our second A1, our B1, and our B2. And we just directly strip right off the character table. Okay. What kind of interactions are we going to have? Well, voila, we have A1s. We have interactions that are going to happen there. And we have a B1 interaction that's going to happen. And we've got this loner out here, the B2, the PY orbital, which has no partner. Right? So that's going to be, we predict right away, non-bonding. Next time, we will mix all these together and generate the molecular orbital diagram for water, and then move on. Okay? See you on Friday.